Hi all, here we discuss about the experiment absorption spectrum of KMnO4. The aim of the experiment is to determine the wavelength of absorption bands of spectrum of KMnO4. The theory behind this experiment is spectroscopy is the study of interaction between matter and electromagnetic radiation as a function of wavelength or frequency of radiation. Absorption spectroscopy refers to the technique that measures the absorption of radiation as a function of frequency or wavelength due to its interaction with the sample. An absorption spectrum shows how much light is absorbed by a solution at various wavelengths. When a beam of light is incident on a transparent medium, a part of incident light is reflected and rest is transmitted. But certain materials mediums absorbs light strongly corresponding to the particular region of spectrum and transmits restes. This is known as relative absorption. The resulting spectrum of transmitted light consists of dark bands called absorption bands. The wavelengths corresponding to each absorption bands are calculated using Holtzmann's formula of absorption spectrum for dispersion. That is, n is equal to n0 plus a divided by lambda minus lambda 0, where n0, a and lambda 0 are empirical constants. It can be also written as mu is equal to mu0 plus c by lambda minus lambda 0, where mu0, lambda 0 and c are constants of the medium. Mu is the refractive index corresponding to the wavelength lambda. The above equation can also be written as lambda equal to lambda 0 plus c by mu minus mu 0. Since there are three constants, there must be three equations for three standard wavelengths, lambda 1, lambda 2 and lambda 3. In order to facilitate the determination of constants, the term mu and mu0 are replaced by linear distances s and s0 of spectral lines from an arbitrary zero value. Thus, the above equation can be also written as lambda equal to lambda 0 plus c by s minus s0, where lambda 0, c and s0 are the Holtzmann's constants given by S0 equal to lambda 1 minus lambda 2 into S2 minus S3 into S1 minus lambda 3 minus lambda 2 into S2 minus S1 into S3, all divided by lambda 1 minus lambda 2 into S2 minus S3 minus lambda 3 minus lambda 2 into S2 minus S1, and C is given by lambda 3 minus lambda 2 into S3 minus S0 into S2 minus S0, all divided by S3 minus S0, and lambda 0 is given by lambda 1 minus c by S0 minus S1. These are the three equations for finding S0, c and lambda 0, where S1, S2 and S3 are the scale readings in the telescope corresponding to three standard wavelengths of mercury spectrum. Thus, the standard wavelengths of absorption bands are given by lambda 1 dash is equal to lambda 0 plus c by S0 minus S1 dash. Lambda 2 dash is equal to lambda 0 plus c by S0 minus S2 dash. Lambda 3 dash is equal to lambda 0 plus c by S0 minus S3 dash, and lambda 4 dash is equal to lambda 0 plus c by S0 minus S4 dash. These are the four equations for calculating the standard wavelengths of absorption bands. Then the potassium permanganate is here used. That is, the potassium permanganate is an organic compound with the chemical formula KMnO4 and composed of K plus and MnO4 minus. It is purplish black crystalline salt that dissolves in water to give intensively pink or purple solutions. Its crystal structure is orthorhombic. Then the procedure behind this experiment is the preliminary adjustments of the spectrometer are done. That is, the focusing of telescope, adjusting of the prism table, etc. Then the mercury light is switched on. The prism is mounted on the prism table and the spectrum is obtained. Initially, the experiment, the adjusting the scale and find the scale readings on the mirror, and the scale readings is found through the telescope. This is the initial setup. Then the telescope is adjusted to be in a minimum deviation position and its crosswire is made to coincide with a given line of mercury spectrum. The scale and telescope is adjusted in a convenient distance from spectrometer. The reflected image of scale from the plane mirror fixed to the telescope is obtained and reading is taken. This is repeated for 3 standard lengths of mercury spectrum with wavelengths lambda 1, lambda 2 and lambda 3. The corresponding scale readings are noted as S1 and S2 and S3. Then the mercury light is now removed and a milky lamp is used as the source, and the given KMnO4 solution is introduced between source and spectrometer. Dark lines corresponding to the absorption spectrum of KMnO4 can be seen looking through the telescope. The concentration of the KMnO4 solution is adjusted to get 3 dark lines using the scale and lamp arrangements as taken before. Then the wavelengths corresponding to these readings can be obtained from the Harman's relation. That is, initially we get a spectrum of consist of red, yellow, green, blue and violet lines. Then the scale readings for corresponding spectral lines are taken, and then when removing the mercury lamp and introducing the milky lamp, we obtain for dark bands, and the corresponding scale readings for dark band is taken as, and using the equations we can find the lambda 1 dash, lambda 2 dash, lambda 3 dash and lambda 4 dash. This is the experimental setup for the experiment. That is, there is a source, a KMnO4 solution and the spectrometer and the prism on the prism table, then a telescope and a scale. Using this setup we can find the wavelengths of the KMnO4 spectrum of the KMnO4. Then the result is the wavelength of the absorption spectrum of KMnO4 are calculated. That is lambda 1 dash, lambda 2 dash, lambda 3 dash and lambda 4 dash in the order of 500 something nanometer. This is the wavelength of absorption bands of spectrum of KMnO4. This is all about the experiment. Thank you.